Hello, this is Discrete Maths, MATH1081, and I'm going to have a look at question 41 out of chapter 4. This chapter is about combinatorial mathematics and using combinatorial ideas. And this section is on recurrences and recurrence relations. This is a hard question 41. It's marked with a star, and so this is a slightly more difficult problem. And it's essentially looking at the number of ways of partitioning or of splitting up the set of numbers from 1 up to n into 3 disjoint, that means they've got nothing in common. I should have written that in here in the question. It's written in the question. Let me just pop this in. 3 disjoint, that means they have nothing in common. And again, this is going to be disjoint. Non-empty subsets. So we start off in the first part with just splitting it up into 2 non-empty subsets. So we're trying to take my S and split it up, take these numbers and split them up into 2 non-empty subsets. Well, you learned back in the very first topic that the number of subsets of S, so the number of subsets of S is 2 to the n. If you've got a set with n elements, then the number of subsets of that set is 2 to the n. Now that may include empty subsets as well. We'll worry about that at the moment. So I'm taking my S and I'm splitting it into 2 sets, A and B. So what I do is I take each of my subsets and I plonk them into A and then put B as what's left over. So we take each of these, so the number of subsets in S is 2 to the n. So for each subset, place it in A and then let B be what's left. So take each subset, shove it into box A, and then take S minus A and plonk that into box B, and that will give me a partition, but of course the A and the B I could flip the other way. So since the order of A and B is unimportant, there are 2 to the n divided by 2, which is 2 to the n minus 1, such choices. And finally, since neither can be empty, so you may have chosen the empty set and plonked it in there and put S in there, or you may have chosen all of S there and put the empty set in there, but that's not allowed. They've got to be non-empty sets. We have to subtract off 1. So the desired number is 2 to the n minus 1 minus 1. And that's what we were asked to show. Now for the second part, we now take the numbers from 1 up to n and we let Sn be the number of ways to partition this now into 3 disjoint non-empty subsets. And this is more complicated because now you're going to take S and split it into 3, and they've got to be non-empty. The order within the sets and the order of the sets here doesn't matter, but they've got to be non-empty. So S1, well, that says you take the number 1 and you've got to break it up into 3 non-empty subsets. Well, that can't be done. So the answer is 0 for that one. Similarly, if you've only got two objects, you can't split them into three disjoint subsets all non-empty, so that one is 0. If you've got three objects, well, you haven't got much choice. You simply put 1 in one of them, 2 in the other, 3 in the other, and that's it, and there's only one way of doing that. Now, if you've got 4, it's a little bit more complicated. For 4 objects, well, you could put 1 and 2 in the first box, and then you've got 3 and 4, or you could have put 1 and 3, and then 2 and 4 in the remainder. The order doesn't matter internally here. You could have put 1 and 4, and then I get 3, or I could have put 2, doesn't matter which order you've got them in. Or I could have put 2 and 3 in there, and then I've got 1 and 4. I could have put 2 and 4, and then I get 1 and 3. Or finally, I could have had 3 and 4, and then I put 1 and 2. So in fact, there are 6 different ways of splitting it up when you've got 4 numbers to split into 3 boxes. Non-empty, and the order doesn't matter. Okay, so just to summarise what we did in the part B, we found the first 4 values of this sequence, 0, 0, 1 and 6. I want to now, part C, we're asked to get a recurrence. It tells us what the recurrence is, but we have to explain how we got there. So remember, we're taking our set S and we're trying to split this up into 3 bits, into 3 subsets that are mutually disjoint. So when I do these recurrences, I like to think of them as, well, suppose I've almost finished. So I've taken n minus 1, so I've taken the numbers from 1 up to n minus 1, and I've split those into 3 disjoint, non-empty subsets. And now I want to put the number n in somehow. So the number n has to get placed somewhere in here, and I can just place an n in either there or there or there. And I've now split up the numbers from 1 up to n into 3 disjoint subsets. So that's one way of doing it. So if I so there are s sub n minus 1 ways of splitting this up into 3. I can either put n there, there and there. So there are 3 different choices there. So to explain what I'm doing here, I would say put partition the numbers 1, 2 up to n minus 1 into 3 subsets that are disjoint and non-empty, and then add n. So there are 3 ways of doing that. Now that, unfortunately, is not the only way in which we can end up with S being split up into these 3. Because we could have ended up with the situation looking like this. This number n might have ended up in this partition sitting on its own at the end. And that would still give you a partition of these numbers into 3 disjoint non-empty subsets, but it's not going to occur from here. It won't occur in this scenario because that would have had to have been empty, and in this, this formula counts the number of non-empty partitions. So how is this going to arise? Well, we would take the numbers 1 up to n minus 1 and plonk them into these 2 sets, and then add the n on at the end. So that's the other scenario that could happen. So here, to explain what I'm doing, I'm going to split S into 2 subsets and form the third using just n. Now, how many ways can we do that? Well, we saw back in part A, the number of ways of splitting a set into 2 was 2 to the n minus 1 minus 1. And so we can now say the number of ways of doing this will be 2 to the n minus 2 minus 1. 2 to the n minus 2 minus 1. So this is using the formula for part A. Okay, so that gets me the recurrence that I wanted, and now finally I have to solve it and see if it find what the general solution is. So we now solve this recurrence, which is a first order. This is a first order equation because we're only going down by 1. There aren't extra terms there. It's a first order recurrence, and it's non-homogeneous because you've got this forcing term on the other side. So to do that, our technique, our method is to look at the corresponding homogeneous equation, which is going to be Sn minus 3, Sn minus 1 is 0. We look at its characteristic equation, which is just lambda minus 3. It's only first order, so you get a linear equation, not quadratic. So lambda is 3, and we can then write down that our homogeneous solution is something times 3 to the n. Only one term here because it's a first order equation. We now try to get a particular solution, and I've got to be a bit more careful here as to what we're going to try. So I look at the form on the other side, and I see that it's a power of 2. It's some power n minus 2 of 2. So something of the same shape would have a constant in front. So that has the same basic shape as that term in the forcing term. And I've got a minus 1 on the end, so I better try adding in a constant. So I try something of the same shape. So I put in a constant there for that one. Now I substitute in. Substituting back into the recurrence, I have b times 2 to the n minus 2 plus c. Now I've got to multiply this by 3 and bump n down by 1. So this is 3 times b times 2 to the n minus 3 plus c. Plus I have 2 to the n minus 2 minus 1. So I substitute that in, and that's what I end up with. And now I have to solve that. I'll leave the recurrence there. I now have to compare and contrast on both sides of here. So it looks a bit of a mess at the moment. I'm going to get all the powers of 2 together, and the smallest power of 2 is 2 to this n minus 3. So I'm going to try and write everything in terms of 2 to the n minus 3, and I'll take that out as a common factor. So on the left-hand side here, I'll have to take a 2 out of here and make that 2b. I'll take this term across the other side. That's already got 2 to the n minus 3 in it. And I'll take this term across the other side, and I'll have to take a 2 out of that one. And I'll put all the constants, I think, on the other side. So I'm going to get 3c minus c is 2c, and then minus 1. Well, how on earth can that possibly be true? Because I've got powers of 2 here. There's no powers of 2 here. I've got constants here, but this is not a constant. The only way that can be true is if all these coefficients here are all 0. So that tells me that 2b minus 3b minus 2 better be 0, and 2c minus 1 has to be 0. This has to be true for every value of n, and so therefore you can equate the coefficients. So this tells me then that my b is going to be minus 2, and if I got that right, I get minus b. Yep, b is minus 2, and c is going to be 1/2. C is equal to a half. I'll just check at this stage that I've got my calculations correct. Yep, so I get C is a half. Righto, so now putting everything together, so therefore the general solution is going to be Sn. The homogeneous solution was A times 3 to the n. We don't know what A is yet. And the particular solution was, that's minus 2 times 2 to the n minus 2 plus C, which was a half. And I might just tidy up a little bit here. So this is A times 3 to the n minus 2 to the n minus 1 plus a half there. Now we don't know what the value of A is at the moment, so I better work that out. We do know that S of 1 is 0. So that tells me this is A. If you put in 1, you get minus 1. And, I need 3 times A. 3 times A minus 1 plus a half. And if I solve that, this gives me a half on the other side, so I get A is 1 over 6. Some rather odd numbers coming out, but that's the way it works. And I'm going to substitute that back in again and finally write down what the final solution looks like. So finally then my S sub n is, now A is a 6th times 3 to the n minus 2 to the n minus 1 plus a half. And again, I might borrow one of the 3's out of here and write this as a half times 3 to the n minus 1 minus 2 to the n minus 1 plus a half. And just to tidy up, I'll take a half out of the first and last terms and write it like that. Now we should just do a little check here at this point. So we saw that S4 was 1/6. Just checking again that I've got that correct. So we know that S4 should come out to be a 6th. So I put 4 in, I get 3 cubed plus 1 minus 2 cubed. So 3 cubes 27 plus 1 is 28 over, that's 14. 14 minus 8 is indeed 6, and that's what it was supposed to be, as we saw back here. And we could now calculate, for example, if we wanted to know how many ways of splitting up the numbers from 1 up to 6 into 3 disjoint non-empty sets, then I could plug in 6. So I'd get 1/2. I'd get 3 to the 5th plus 1 minus 2 to the 5th. So let's see, 3 to the 4th is 81, so that's 243, that's 244, that's 122, minus 2 to the 5th is 32, and that gives me 90. And so there'd be 90 ways, in fact, of splitting up the numbers from 1 to 6 into 3 disjoint non-empty sets.